Hello, everybody. It's a pleasure for me to introduce Dmitry Kopitkov. Dmitry obtained his bachelor degree in 2012 from a computer science department. And then he proceeded to his master's degree here in TASP under my supervision. And during that time, he was awarded twice the prestigious Irwin Jacobs Excellence Fellowship and graduated summa cum laude. And he's been pursuing his PhD research starting since 2017. Okay, Diman, go ahead, please.
Thank you, Vadim. All right, so you see the presentation, right? This file here, everybody see it. I will start. So hello, my name is Dmitry Kopitkov, and I'm going to present my PhD seminar, which is named General Probabilistic Surface Optimization. The work was done under the supervision of Professor Vadim Iderman. All right, so straightforward in the problem that I will talk about today, consider two PDFs, probability density functions, which I abbreviate here PU and PD. We'll later see why I chose this abbreviation. And consider two data sets of ID samples from these two densities. Statistical analysis of these two data sets involve different problems. Various statistical problems are required to be solved. Like, for example, density estimation, conditional density estimation, ratio of these densities, and many more. And it is required in many different domains, like robotics, computer science, economics, and so on. These problems are very frequently required to be solved. More particularly, if we have this available dataset of ID samples, we may want to approximate or learn the PDF function that it generated these samples. And it is required in problems like measurement likelihood model in robotics, or estimation of distribution entropy, or even in image denoising. There is also a requirement to learn first this prior or the images. Likewise, if we have two datasets, we may want to estimate this ratio, PU divided by PD. And it is required in anomaly detection or divergence learning, which is frequent in generative models. And further, learning these target functions in logarithmic scale usually is much more numerically stable. And more general view of these target functions can be a sort of a sum function T, which gets these two inputs. So we can express these target functions with such general form like written here, and we can express much more other target functions that we may want to approximate in different applications. And there are many works on this topic, how to approximate different target functions T. And there are many works that for each such target function suggest some objective function that you can use to learn the corresponding statistical modality. And this will be my main focus of this entire talk. So some related work in this domain. There are many frameworks for estimation that are based on divergence, like Bregman divergence and F divergence. Maybe some of you know the F-GAN framework, which is very popular in the GAN domain. And there are also many divergence-based objective functions, like maximal likelihood estimation or noise contrastive estimation, energy-based anomalized models, critics of GANs, as I already mentioned, and many more. So again, there are huge amount of literature that provides various objective functions to learn different target functions that you can express in this general form. Now, the goals of my research that I put before myself when I began this work were directed in two main topics. Statistical inference, where I would like to understand a deeper relation between different probabilistic modeling methods, how they are related to each other, proposing a new objective function which may be better than the existing ones. And the important part would be make it easy and intuitive, because currently lots of this work require you to know a lot of mathematical background. So I will talk about some more general framework, which is also be very simple to understand. And the second direction, deep models. I would like to apply neural networks to learn various probabilistic modalities and to understand its gradient-based optimization dynamics. Understand its aspects like generalization, interpolation, bias, variance, etc. And the contribution of this research, PhD research work is following. So again, we have two directions. The main direction is statistical inference, where I produce the estimation framework, which I call Probabilistic Surface Optimization, PSO. And it provides, it allows to generate infinitely many objective functions to learn almost any target function T, as we'll see later. It also provides systematic and very simple theory under the unsupervised learning, and it likewise allows to mechanically recover the existing and known statistical objective functions. In the direction of deep models, I will relate the PSO performance with the model kernel, which is also known as neural tangent kernel, NTK. And I will also analyze the dynamics of this kernel, and it depends on neural network architecture. So all these topics, I will talk about them today, and I will talk about some very shortly. You can find more details in this paper here. Okay, so let's start with the PSO formulation, its more general view and its derivation. Consider a function space, this big F here, which contain functions of this form here. So they get basically Rn input and return this color. And theta here is the parameter vector. So maybe, for example, neural network, where this is the parameters of the neural network. And the main idea is to view this function as some representation of a geometrical object, which I call high-dimensional surface. So it can represent some surface in high-dimensional space, where the support of this surface is this Rn. So for this picture, we can see two-dimensional support, and the height at any point at the support is the output of the function. So basically, our function is just a representation of some geometrical object like this. And the main preliminary introduction of my framework will be following. I will show how we can push this surface in different directions with some forces Fu and Fd, force up and force down. So our symbols U and D are actually symbolize some direction of forces. And I will enforce it to converge to any desired target T. So we will see what are these forces and how can we do it in later slides. Okay. So more formally, let's define two densities, Pu and Pd over Rn. With identical support. It's not required identical support, but there are some specifics that I need to talk about them. In a case where this support is not identical, and I will not talk in this presentation about these subcases. Consider two corresponding data sets, xui and xdi, generated by these density functions. Likewise, choose two magnitude functions that have this shape here, this signature that you see here for both of them. So mu and md functions, we will call them magnitude functions. We'll see later why I chose this name for them. And here is important step that we are actually choosing these functions. It would be our choice that will control the later on a convergence of the algorithm. And finally, Let's perform this gradient descent, the usual gradient descent algorithm that updates theta in following simple way. So here we have learning rate, and d theta is having this shape here, right here. So we can observe two averages here over samples xui and xti, ID samples from our distributions. We see here the magnitude functions mu, md, model gradients, and note there are different signs here, minus here and plus here. And PSO framework is basically states that just perform the gradient descent optimization with the given update of theta. And the claim is that at the convergence, our steady state function to which we will converge, f star, will satisfy this equation. Pu multiplied by mu equal to Pd multiplied by Md, and it will be called PSO balance. This equation is actually the main point of the entire algorithm. It will allow us to learn different modalities. All right, so let's next derive this framework in some simple way. Define the PSO loss as following. So we have now a new functional that is defined over functions, and it has this shape here. Again, we see two expected values over Pu and over Pd, signs minus and plus, and now we are having here two other functions, mu tilde and md tilde, which are antiderivatives of our previously chosen magnitude functions. The functional derivative of this equation, which if it's equal to 0, will produce the Euler-Lagrange equation. It basically says that the optima of our functional f star will satisfy the Euler-Lagrange equation, which is, it's not really hard to show that it is just this balance state I showed before. So basically, this equilibrium that I claimed before is just Euler-Lagrange equation of this functional that we defined. Next, I'm proposing just to solve this optimization. Let's find the function that minimizes this functional. So I'm taking some function space with functions parameterized by theta and solving this problem, optimization problem, which basically goes to gradient descent. Usually we do it with gradient descent algorithm, which requires the gradient of the loss with respect to theta right in here. So again, we can see here two expected values. mu and md define some variational equilibrium that was shown before, the Euler-Lagrange equation. And now we also have this model gradients, and they actually define the metric over the function space. I will talk about them more at the end of the presentation. Now, the final part is just to approximate this population loss gradient with the sample approximation over the samples that we obtained. So this is the d theta that we saw before, and it concludes the derivation of this framework. So again, we basically in PSO minimize some functional whose Euler-Lagrange is written by this equality here. The main points to note here is that mu and md control the convergence f star. So for different choices, we will get different convergences. Likewise, the mu tilde and md tilde are not required at any point of this algorithm. So basically, they are appearing only in the mathematical proofs, but they are not required for any step of this algorithm. And we basically define any PSO instance by these two functions. So we can say that we are defining our estimators via the Euler-Lagrange equation. This identity can be used again to estimate many different modalities. And some part I didn't tell, the magnitudes must satisfy some sufficient conditions, so you can find it in the paper. They're not very strict, these conditions. All right. Next, I will talk about the physical perspective of this framework, which I think the main advantage of this framework. It provides strong intuition and you can use it to understand the optimization dynamics. Okay, so as I already mentioned, our function is just a representation of some high-dimensional surface. Function space that we chosen for our optimization can be quite many choices. We can use neural networks like fully connected CNNs, ResNets, and so on. It can be also RKHS, partition kernel Hilbert space, which is just a linear model in some feature space defined by this kernel here. And important property of any function space in the context of gradient descent is the kernel that looks like this. So dot product of model gradients at two different points. This kernel is responsible for interpolation and extrapolation during the gradient descent. It is known as neural tangent kernel in a neural network domain, and for RTHS it's just equal to this repetition kernel. All right, so the next part to understand before we talk about the physical system perspective is the update of this simple form here. So let's take our theta and add to it some model gradient at some point x. Then we can show that at any other point x tag, the function, our model, changes according to this kernel here, the model kernel. And this is the first order Taylor approximation. So this is actually usually very close to be true. In other words, we can say that when we push or optimize at some point x, our model at any other point x tag changes according to this kernel approximately. And we can also think about this update as we push at some point x with some pushing stick or pushing wand that we are using. The shape of this pushing stick is described by this kernel. So basically, the function space that we are taking when we are starting our optimization defines these pushing sticks that we are using during the optimization. And different examples can be made. If it's RKHS, then we can think about Laplacian kernels with different bandwidths or Gaussian kernels. Neural networks have very strange kind of shapes. Also, we'll see it in the end of the presentation. And the main question is, now that we have this tool of pushes, can we push our surface to any desired shape? And the answer is a positive. And let's see again our update of theta. So this was the original idea that allowed me to construct this PSO framework. The update that we are actually performing during the optimization is shown here, and we can observe that there are linear combination of model gradients at points xui and xti, which can be interpreted as we are pushing up at points xui, up because it moves here, and down at points xui, xdi because it moves here. And our forces, like some forces are applied on our physical surface, our forces are magnified by outputs of mu and md. And again, this gradient, the model gradient and the model kernel serves as some sort of sculpture tool that we are using during this physical system optimization. Next, if we are taking two specific limits, then we will recover our variational equilibrium. That is, if we are considering that we have infinitely many data points and the bandwidth of the model kernel is infinitely small, so it's, namely its delta function, then we can think that on our surface we apply at any point many pushes up and many pushes down, and the forces up and down can be expressed via these equations here. So we are pushing up with force that are a product of Pu and Mu, and we can intuitively think that we push it up stronger if we have more samples from Pu, and if the output of Mu is larger, and same intuition goes for the down force Fd. And such a perfect physical perspective will be at equilibrium only when the pointwise forces are equal, Fu equal to Fd at any point x, which, if we are looking at these expressions, is basically the variational equilibrium that we saw before, basically the Euler-Lagrange equation. So to conclude, if we would have some very perfect physical system with many training points and the bandwidth of our model kernel being very small, basically infinitely flexible surface, then we would achieve the variational equilibrium. In actual optimization, the equilibrium is very strongly depends on properties of the model kernel and number of points. So this gradient descent equilibrium is somehow close to the variational equilibrium, but it's not exactly the same. We'll see more information about this equilibrium later on. Okay, so now let's start talking about the variational equilibrium and its applications. How can we use the piezo bound state for inferring of different statistical modalities? Consider these two magnitude functions, mu equal to 1 and md equal to f. So this particular choice of magnitude functions, and to understand what would be our equilibrium, we need to solve the piezo bound state. So the piezo bound state can be shown as ratio of densities is equal opposite to ratio of magnitudes. And if we substitute this expression inside, we will see that f star is equal to pu divided by pd. So basically, we got ourselves a method, estimator, that learns density ratio from the available data points. And this actually already belongs to some existing laws, which is called ULCF. Next, let's change a little bit the setting. So instead of constant 1, we will change it to be equal to pdx, mu equal to this function here. And the scenario is following. Pux we don't know, but we would like to learn from its IIT samples. And PD would be our choice, our auxiliary distribution, which we can use, which we can choose. It can be uniform or Gaussian, and it will create the downforce, the balance force to create the equilibrium. Introducing this magnitude function into piezo bound state will create this equilibrium here. So f star will be equal to pux, and we got ourselves new method for density estimation, which I once called dpdf for some reason. Okay. So next, let's see the demonstration of this framework for this particular magnitude functions. Again, we will learn PU from its samples, and PD is just auxiliary distribution. PD in this example will be a uniform distribution over some two-dimensional support. PU will be this will have the same support, but will have these columns shapes. And again, our task now is to push our surface to have shape of PU by using the described piezo forces. So let's see the video of this particular experiment. Okay, so so this is the usual optimization of models. So you can see that so I did some kind of forces that are applied over our model, that pushing it up and down. It vibrates around the target function, and this vibration happens because of this all these statistical forces that are stochastic forces that are applied on it. And the main idea is just to reduce a little the learning rate monotonically, so this vibration will be smaller and smaller, so that it will converge to the exact target function. Okay, so this is it. Let's get back to the presentation. All right, so this is the main idea of entire framework. And again, I emphasize every kind of PSO instance is just defined by different magnitude functions, and the same equilibrium, the same physical system is happening. So there's no real difference, no big difference between different PSO instances. And this may unify different methods because they are just instances of this framework. More general view of this framework is following. Let's define these following two functions, R and T. R would be the ratio of magnitude function that we are defined before, and T is the function that we are approximating. It will express our equilibrium. The main idea is to understand that these two functions are related via inversion with respect to second argument. So one is inverse of the other, and here I wrote what is the meaning of inverse functions. So this allows us to create now a PSO instance, PSO estimator to approximate any T as follows. Consider target function that you would like to approximate that expressed by some function T. First, let's find its inverse with respect to second argument and call it R. And second, let's find two magnitudes mu and md whose ratio is this R. For example, let's construct now new methods to approximate log PUX. For this, we can already see that the PSO convergence T is expressed by this mapping here. So if we are a substitute PU, PD instead of Z, we will obtain log PUX. So this mapping expresses the modality that we would like to learn. Now, the inverse of this function with respect to second argument is written here. And a smaller remark about the inverse functions, usually the involved functions T and R for different applications are very simple. So to find the inverse, it's not problematic. It's usually a very simple task. Next, now that we have this R function, we can offer any two magnitude function mu and md that satisfy this equation here. So we basically use the R and substitute it in at this side. All right, so any two magnitude function that satisfy it will give us the equilibrium at log PUX. And for example, we can take md equal to xf or mu equal to pd, and it will produce such equilibrium, but there are actually many more choices that we can do, because if we are multiplying both magnitudes by some factor, it will be canceling out each other. So we basically have infinitely many different magnitude functions that can be applied here. Next, so let's summarize the relation between R and T. R and T are very important, the main mappings of this framework. The magnitude ratio R and PSO convergence T are related via one-to-one connection. So knowing one, you can find the other. The PSO magnitude pair mu, md, and ratio R have a one-to-many relation. So infinitely many different magnitudes will give the same R. And for this reason, we have infinitely many magnitude pairs that will give us the same equilibrium. So basically, we have infinitely many estimators to learn any function T. Likewise, there are some legendary transformation relation between R and T, which I will not talk about in this talk. And the main question is which PSO instance or which magnitude pair should we choose? So we have infinite number of them. Which is the better? And currently the answer is unknown, really. I don't know which is the better. But one property can be experimentally evaluated to be true, which is boundedness of magnitude functions. So as we saw at the beginning, mu and md are involved in gradient of the loss. So if they output some very large outputs, it can create a very large gradient, which will make the optimization unstable. And PSO framework allows to bound any two magnet functions to learn any t. So consider specific magnitude functions which have some convergence described by function t. And now we can create two new bounded magnitude functions as following by these transformations here. So from this construction, we already can see that the new functions are bounded between -1 and 1. Other norms also can be applied. So here we basically use norm 1. And the interesting observation is that many of the popular losses, if we are calculating their functional derivative, we will see that their magnitudes already bounded. So noise contrast estimation, logistic loss, cost entropy already have this kind of normalization inside of their magnitude functions, which may explain why they are so popular. Possibly they are better than other alternatives. They're more stable. Okay, so to summarize the work till now, PSO framework allows us to infer numerous statistical modalities. In similar manner, we can learn any function of PU or of this ratio or any function that we can describe in this shape here. It allows simple, intuitive perspective as a physical system with some virtual forces applied on it. It's surprisingly easy to understand. And once you get this idea that we just basically push some very flexible surface, this intuition can let you to create very interesting losses actually. Further, we can mechanically recover almost all existing objective functions for density estimation. And I'm saying here almost because currently I don't know any object function that is not in this framework, but maybe they are. Cross entropy and critics losses of most guns are also in this framework, so we can recover them for specific magnitude functions. And conditional density estimation is also possible by applying Bayes' theorem, which is the details can be found in the paper. All right. So back to the gradient equilibrium and relation to model kernel. We saw that variational equilibrium can be quite useful. It can help us to estimate many different statistical modalities, but actually the equilibrium is only theoretical. We not really achieve it when we are performing the real optimization. In reality, we are having some other equilibrium, gradient descent equilibrium, and now I will talk about this equilibrium and how can we understand it and what are the consequences. So the function in a function space can be expressed, its dynamics can be expressed by this equation here. So I replace theta by t, so to represent the time of optimization. And now our function is evolving in time during the optimization via such a differential equation. So it can be viewed as following. Ft, we can think about it at some point in infinite dimensional vector space. So function space is basically infinite dimensional vector space. And Ft is just some point in this space. Ft is the functional derivative of the loss. So it's related to Euler-Lagrange equation. And for our PSO loss, it has this form here. So some nonlinear transformation of small ft. And here we are still in an asymptotic regime where we have infinitely many data points. We can bound it to the real finite data set regime, but I will not talk about it today. So this part, this FFT, is just the steepest direction in a function space towards our minima of the loss. Just direction where we should go to achieve the global minima. And this global minima is basically the function that satisfies the Euler-Lagrange equation. Further, GT is the integral operator with respect to model kernel described here. and we can think of it as just an infinite dimensional matrix. So we basically have here a matrix vector product. And the question is how GT affects the inference. So what are the properties of GT, and what should we expect at the equilibrium? And the simple observation is that our equilibrium changed. So before we use this Euler-Lagrange equation, functional derivative equal to 0, which produced the balanced state that we used for different applications. But now we have this equilibrium here. So basically matrix vector product equal to 0. And this says that we basically allow our functional derivative to be in the null space of G infinity, which typically happens during optimization, and it produces the bias over our solution in most cases. Other observations over the role of gradient separator in these dynamics are following. So here are some insights that you can see also in other papers. I'm not claiming that I'm discovering all of these insights, but I also saw it in my work, and we will require it for the final part of the presentation. So GT is just serving as symmetric over function space F. Its eigenvalues, eigenfunctions of a model kernel define in which direction it's easy to go and in which direction it's very slow. So the eigenfunctions with the largest eigenvalues are the directions where we can just progress easily. And the main part is to understand that the alignment between the steepest direction and the top eigenfunctions is basically what defines the optimization outcome. So if they are aligned well, so if the steepest direction towards our minima, global minima, is inside this top eigenfunctions of the model kernel, then we basically can achieve our global minima. If not, then we will project to some subspace and we'll stop there. And it's in reality happens. Like you can check it with experiments, and you will see that this is the actually behavior that happens during the optimization. And the main part here that in kernel methods, RKHS literature, you can find many different works that are suggesting how to produce kernel that aligns well with the target function. So how can you now produce the kernel maybe as linear combination of existing kernels such that the new kernel would align better with, for example, labels in some regression task? There are many works on this topic, and surprisingly, in neural networks, it happens already implicitly during the optimization. So this would be the final part of my talk. Consider the following experiment. A regression task where we would like to learn this F star function. So this function, Mona Lisa function, has two inputs, x1 and x2. And the output is the gray level of the pixel, and we would like to learn it via some neural network F theta. We will take a lot of samples of input points and the labels and perform the least squares regression for long time of gradient descent optimization. And the goal of this experiment to understand how the model kernel, GT, and its eigenvalues and eigenfunctions change along the gradient descent optimization. So one particular important observation is the following. For a Lickey-Relu fully connected neural network with 6 layers, we can draw the eigenfunctions at the time 0 at the initialization of neural network, and we can see that there's nothing special about these eigenfunctions. It's like some rays of light. There's some notion of frequency, so information has more of frequent nature when we are continuing with the index, but other than this, there's nothing special to tell about these functions. After several thousands of iterations, we can see that these eigenfunctions already very much resemble the final, the target function we are learning. Further, if we are drawing this kernel around some point x, marked by red plus here, so then again, we can see that this model kernel doesn't have a very interesting shape. has some local structure around the point, but still just the rays of light as we saw before. And after some iterations, we already see that it aligns very well with the target function that we are loading. So the outcome of this experiment is following. We saw the strong evidence that top eigenfunctions of the model kernel aligns with the F star, which increases movement speed into direction of F star in the function space F, as I explained before. And intuitively, if we are talking about this physical system and with pushing sticks that I described before, we can say that our sticks that we are using, they are pushing the surface to some target function, but at the same time, they are also aligning their shape so that they are aligned better with the target function, which increases the performance, which improves the performance of the optimization. Likewise, we saw that neural networks with more layers have higher alignment, which may explain their top performance. And we also saw the same alignment in SGD, Adam, and different piece of learning hosts. You can find more information in this paper here. So to summarize, we saw a piece of framework which allows to learn almost any target function T, and proposes for these infinitely many estimators. There's strong intuition behind this framework, which allows to use piece of concepts for various numerous applications. The actual equilibrium strongly depends on properties of model kernel. And I didn't talk about many topics that are relevant to this aspect. In the neural networks, model kernel aligns itself with the target function for currently unknown reasons. In future work, there are many questions to be answered. So, for example, which piece of instance should we choose? There are infinitely many of them, and which one is optimal? What is optimal? How it's related to the kernel? It goes to the direction of robust statistics, and it's very important question. Likewise, convergence rates, how fast we are converging into the null space of gradient descent operator. Impact of model kernel is small data set setting. And once we know the answer for these two questions, once we know what is impact of model kernel on our performance, this following question will arise. So now we will know what are desired properties for model kernel to have. The question, can we now architect new neural network that can satisfy these properties? And this would be probably a very interesting question to answer. Likewise, regularization high dimensional space for small data set, also important question. All right, so that's it. Thank you for listening. Any questions?
Thanks, Dima. So we have time for questions. Go ahead, please. If anybody has a question, just ask. We have plenty of time, so feel free to ask questions.
Yeah, talk too much fast. Sorry, too much content also.
I have a question.
Yes.
Sure.
So,
1 second, I just put the headphones. I will hear you better. Yes.
regarding the magnitude functions, so according to your proof, they need to have your proof goes through the antiderivatives of the magnitude functions.
Well, it's more complicated. I skipped some parts that I didn't have time to talk about them, but one of the proofs is via calculus of variations. Let's see the slide for this. Yeah, so I defined some functional that has this form here, and I defined the antiderivatives. So if we are talking about the Euler-Lagrange equation, it will produce this equilibrium.
Great. So it means that for this proof to be valid, they need to have antiderivatives, meaning that
Yes.
magnetic functions you choose are constricted to have antiderivatives.
They are even more so. I am considering them now to be continuous functions, which already gives you this property that they have antiderivatives. So basically, if you go into the paper, there are two pieces of frameworks. One is for this function to be non-differentiable, and it will give you much more wide spectrum of approaches. And then there is a place where I'm talking about this function to be differentiable, and then all this kind of framework goes into the place. So if I'm assuming this to be differentiable, so then of course mu and md have also the antiderivatives. There are some additional sufficient conditions that mu and md should satisfy, and this condition, like for example, the continuity in some specific domain will ensure that this mu tilde and md tilde exist. But you don't need to know them. So this is the strength. For some functions, the antiderivative is like to calculate the integral, and integrals are not very easy to calculate. So when you differentiate some function, it's kind of easy to know what is the derivative of function, but the other way around is more difficult. So now this entire framework allows you to suggest mu and md such that you even don't know the closed form of mu tilde and md tilde.
Okay, thanks.
Okay. Anybody has another question? We still have time, so feel free to ask questions. All right, so let us thank Dima again. Thanks. And that concludes that seminar. Thanks a lot.
All right. Thank you
Bye,
for
everybody.
listening.
Thank you.
Thank you, Leon.
Bye.